As a program committee chair this year, I'm very honored to introduce our first keynote speaker, because we have two. Our first keynote speaker is Andreas Baumann. Please come in front, from the University of Vienna. Andreas is assistant professor in digital linguistics at the Department of German Studies. He has a master's in general and applied linguistics, but also mathematics. In terms of research interests, Andreas has cognitive and evolutionary linguistics, quantitative linguistics, including mathematical, computational, and statistical modeling, epidemiological, ecological, and evolutionary models in diachronic linguistics, linguistic diversity and drivers thereof, like digitalization and colonialism, and also language, data science, digital humanities, and digital humanism. And Andreas, thank you very much for joining the conference as keynote speaker, and we are looking forward to hear you. The floor is yours.
Thank you so much for the kind introduction, and of course also for the invitation. It's a great pleasure to be here. All right, what is this about? So what I want to talk about today is linguistic innovations. As a matter of fact, language changes all the time, and you see this, for example, in sound change, in syntax, changing inflections, but maybe most evidently, you see change in words. And for example, when you look at the Oxford English Dictionary, so they from time to time come up with new entries, and some recent entries are frontmost, so the adjective frontmost, the one thing at the very front of something, the verb to cosplay, so dressing up some character in a movie. Actually, in this event, in this event pyramid here, also cosplay events take place from time to time. And also the noun trash panda. Okay, now there was already some sort of spoiler in the beginning. How many of you actually know what a trash panda is? Now you know. Okay, so let's say 20% or so already knew before. So this is a trash panda. So actually a trash panda is a different word for raccoon. More precisely, a raccoon, especially one that forages in garbage cans. And when you look at at this word's frequency trajectory in diachronic text corpora, so here I looked at Google Ngrams, you see something like this, namely that the word raccoon has sort of skyrocketed in the past 10 or 20 years or so. Now, okay, now the thing is, language is not just represented in text corpora, but it is actually also used by speakers, right? Now, what I want to do is I want to view language change as a spreading phenomenon. What does this actually mean? So a couple of assumptions. First of all, I assume that individuals, so speakers, are part of a population, of a speaker population. And when you look at the particular innovation, then you have individuals that already know a certain innovation. Those are the users of the innovation, let's call them users, and others that do not yet know it, non-users. Okay, and I also assume that individuals interact with each other based on some contact network, some population structure. And I also assume that whenever a user and a non-user meet, then the innovation can be passed on to the latter. All right. So this corresponds to a scenario like this, where individuals sort of shape a population with an underlying network structure. You see this here. So here the dots resemble individuals, speakers. Some of them are connected to each other, others not. And at the first time step, just one of them is a user. Okay, and then after some time, maybe two more adopt a certain innovation, and then if you wait some more years or whatever, you see that even more learn and use that innovation. Okay, now the big question for today is, can we model the spread of lexical innovations through speaker populations with methods from epidemiology, and in particular methods from mathematical epidemiology? And this then will allow us to address questions like this. So first of all, it's at what pace do lexical innovations spread? What drives innovative semantic usage? And who is actually responsible for the propagation of innovations? And this essentially is the menu for today. So 3 different case studies that I want to cover. But before that, a brief primer in mathematical epidemiology. So almost 100 years ago, two researchers from epidemiology, Kermack and McKendrick, they have observed that diseases sort of are passed on from infected to susceptible individuals, and that this can be modeled in quantitative terms. And what they did was they modeled the growth of the number of infected individuals by means of certain mathematical object or construct, namely an ordinary differential equation, abbreviated as ODE. Okay, and they found that the solution of this ODE is a logistic curve, so an S-shaped curve that goes like this. And you probably know this, and I will come back to this in a minute. What is important to note is that this model here, which is sort of a standard model of mathematical epidemiology, is referred to as SIS model of infectious disease, so susceptible, infected, susceptible. All right. Now, about half a century later, this model was transferred to the study of language evolution, actually through 2 different routes, interestingly. So the first one is the field of quantitative linguistics, where Piotrowski and colleagues and Altman in the 70s and 80s have studied S-curved dynamics. So they have observed S-shaped curves in linguistic change, and they actually use this model, the EPI model, to model that. The other route was through the sort of the study of cultural evolution, in particular by Cavalli-Sforza and Feldman, where they actually applied this SIS model to the transmission of cultural traits. And these cultural traits could be linguistic variants. There are many subsequent direct applications of the model, but unfortunately, we don't have the time to delve into all of them, but just a few. Now, first model. So this is actually the first equation out of 3 in this talk. So no more. Actually, it's 5 equations, but 2 are not that important. So it's just 3 that are relevant. Okay. So what does this model look like? So essentially, this model is a set of 2 equations, not super complicated equations. And what they do is they trace the change in the number of non-users and users. So the first equation is for non-users, second equation is for users. So this is what you see on the left-hand side here. So those are the 2 change rates. And then on the right-hand side, essentially what you see is, so the details are not that important, but what you see is that non-users can become users at a certain rate whenever they meet. Users can stop showing a certain linguistic behavior for whatever reason, because they do not want to use it anymore, or they forget it, or whatever. And users can die, and they can also be born. So essentially what this model does is it models the switching between 2 different classes, non-users and users. And the strength of a model like this is that we can use it to make predictions about things that are probably not so easy to understand because of the presence of multiple factors that are actually interacting here. Yeah, and we could, for example, address this question here. So let's say you adopt a new word, like raccoon, sorry, not raccoon, like a trash panda or a frontmost. And the question is, how many people learn it from you? So what would you say? Brief estimation. So show the number of people with your fingers. 2. I see 2 here. 2, also 2, 3, 5, 2, 4, 1. Yeah, and what's interesting actually is that only 10 people or so raised their hand. So I assume that for all others, it's actually not that easy to have a clear intuition about that. And maybe for the first ones as well. I don't know. Now, what can we do? So to tackle this question, the idea is to investigate a quantity that is actually well studied in epidemiology, and to look at this on the world level. And the quantity that I want to look at is referred to as the basic reproductive ratio. I mean, maybe you still know it from our previous collective experiences with COVID-19, where in the media this number was also sometimes reported. Okay, so let's have a look at what this actually is. What was that? So the basic reproductive ratio, abbreviated as R0, is the number of secondary cases per new infected individual. So what does this mean? So this means that R0 sort of collects all new cases that one individual induces across the infectious period. And it has a nice property. Whenever R0 is greater than 1, then you see that the disease spreads. And whenever R0 is smaller than 1, then you see that eventually it's going to die out. So this is what R0 means. And now, what does this number actually mean when you transfer it to linguistics? Then it means the number of individuals that adopt an innovation from a single individual already knowing it, on average. And actually, this is exactly the quantity that we wanted to know, right? So this is exactly the quantity that we need in order to answer the question that I've raised before. Okay. What can we do? How can we estimate R0? Now, the nice thing is that in mathematical epidemiology, you have sort of standard results about estimating R0. And there are actually a couple of routes for estimating it, but I will look at 3 different ones. You can estimate it through prevalence data of diseases, through data about age of first infection, and by deriving the intrinsic growth rate of a certain spreading phenomenon, a disease, from time series data that you have, so about incidences and prevalences. Okay, so, and the nice thing is, and I mean, I won't go into detail about this here, but the nice thing is that for each route, we actually have a pretty simple equation to come up with the estimate. Now, can we transfer this to linguistics? Well, we can. Then we would look at the fraction of users of a word by considering prevalence estimates, lexical prevalence. We can use age of acquisition data to look at the lexical age of acquisition. And we can also derive intrinsic growth rate by looking at diachronic text corpora. So all of this can be done. Okay, of course we need data for that. And in my study, I looked at I used all 3 routes of estimation for 4 different languages: English, German, Spanish and Italian. And to derive estimates, what I needed to do is I actually needed to combine a whole lot of different data sets. Age of acquisition data from all languages, prevalence data. I also needed to use the acquisition data to derive prevalence for all languages other than English. I needed diachronic corpus data, corpus of historical American English, and also from Google Ngrams for all other languages where I actually couldn't get access to much better data. Okay, and now when you do this, when you combine these equations, so the formulas with the data, what you see is this, namely that R0 is mostly somewhere between 3 and 14, on average about 6. For English and Spanish, we actually get reliable estimates, converging estimates. For German and Italian, this is not so much the case. And this has a lot to do with the quality and the quantity of the data that are available for these two languages. So what does this mean? During your lifetime, each innovation is passed on to about 6 other people. Considering that in order to have a stable population size, each individual needs to produce about 1 offspring. This means that there are 5 people that you sort of infect with your words. And given that you get to know about 600 to 700 people during your lifetime, this is actually not a lot. But it actually matches pretty well the estimates that some of you have shown with their hands. Anyway, first question resolved. Let's move to a different topic. All right. It is quite evident that words change their meaning. And this is visualized in this graph here. So what is this? You see a triangle here. And this triangle is a representation of a semantic space, namely of the semantic space that is available for words with 3 different senses, according to the Oxford English Dictionary. And each line here corresponds to the semantic movement of a word. The closer in the center you are, the more polysemous a word is, and if you are in the corner, in one of the 3 corners, this means that a word has more or less only 1 meaning. It is not so important how exactly this works and how I came up with this plot. You can have a look at it in the paper from Stefan Hartmann and myself that is going to be published actually in 2026, but it's already there actually. Anyway, what is important is that these trajectories here belong to frequent words, and whenever you look at frequent words, you see movement patterns like this. When you compare this against the dynamics of rare words, however, what you see is that the pattern looks very different. So there is a crucial difference between the 2 patterns that you see here. So it seems that frequency plays some role in semantic change. As a matter of fact, this was studied not only by us, but also by others. But this suggests the question, what drives semantic change? Okay, so second case study. Let's look at the drivers of semantic change. So it is quite evident that words typically have multiple senses. Actually, this is the rule rather than the exception. And logically, these senses must have emerged over time as innovations, and I will refer to this emergence of new senses as diversification, semantic diversification. Let us consider the word mess, for example. Through the past 700 years of the history of English, mess has referred to a portion of semi-liquid food. Okay. However, later the word has gained additional senses. On the one hand, what you see is senses that are related to the food meaning, so a quantity of milk and food and a large amount or a quantity of something more abstractly, but also here extensions like a company of people eating together, a building or room providing meals and having one's meals with a particular person. Okay. What we have in addition is senses like this with actually a pretty negative meaning. So you have here a situation that is confused and full of problems, making something untidy or dirty, a dirty or untidy state of things or place, or to mishandle an enterprise. Okay. Now, how can we address this? So how can we actually study the potential drivers of semantic diversification? This is what I want to do, and I will again use population dynamic modeling as before. Some potential drivers that have been suggested in the literature are frequency, so token frequency. We've seen this in this triangle comparison. Semantic discriminability, so the ability to discriminate between senses. This is a cognitive aspect. And non-conformism, so the tendency not to behave as the majority does. This is a socio-pragmatic mechanism. And now the idea is, again, to set up a population dynamic model, but here not of a single variant, but I want to model competing variants. So how do we start? So first, we model the usage of a single variant depending on some semantic property in a speaker population. The variant could be the word mess, with the meaning portion of food, and the semantic property could be valence or sentiment, from negative to positive. And now what I want to do is I want to study not just one variant, but two variants, and I want to study the competition between them. So then a second variant, mess, denoting disgusting portion of food with a slightly lower valence. Okay. Okay, now second model, second equation. This now looks a bit more complicated. Again, details are not extremely relevant. What is important is that we again model the change in the number of users, and that this is what you see on the left-hand side. On the right-hand side, what you see is that this change is determined by frequency, by the semantic property, by socio-pragmatic factors. So we have a conformism bias here and a non-conformism bias here that enter the equation as terms that reflect positive frequency dependence and negative frequency dependence. And what you also see that these biases sort of depend on the semantic difference between two variants, and this in turn depends on discriminability between different senses. Again, it's not super important, but what is important is that this is sort of a well-defined equation that is although not extremely complicated. So we can tackle it analytically. That's the important thing. And what you can do is you can analyze this model and then make theoretical predictions about the long-term behavior of that model, of the semantic property. And what you find is that semantic diversification can actually happen. Semantic diversification corresponds to a branching process that is shown in this graph here. So here on the horizontal axis, you have the semantic property. On the vertical axis, you have time. And at some point, the semantic trait splits up into two different variants that can coexist stably. Okay. And when does this happen? Well, this happens whenever words have low frequency, when individuals are equipped with high discriminability between senses, and when there is a strong bias to use language in a non-conformist way. So these are the theoretical predictions. Of course, we also need some evaluation. We need to test the theoretical predictions that we made. And for this, again, I need a combination of different data sets. I will very briefly go through them. So I needed sense distributions for several thousand words derived from the Oxford English Dictionary and the corpus of historical American English. Pre-trained embedding models, word frequencies taken from Koha and the corpus of contemporary American English, frequency ratios from different domains, Wikipedia, Coca, and song lyrics to account for non-conformism and conformism biases, concreteness ratings and sameness ratings to account for discriminability, and also a couple of other smaller resources. But all of this is necessary to test the model. And what you actually see when you do the statistics is that everything turns out to be exactly as predicted by the model. Namely that low frequency, high discriminability, and non-conformism promote semantic diversification. All right. Final topic, age, structure, and language change. Okay, so what is this about? So in the literature, there is sort of a vivid and ongoing discussion about which demographic group actually drives language change and how age structure impacts cultural transmission. And depending on your theoretical camp, children, adults, sometimes young mothers, and adolescents have been proposed to play a key role here. So the question that I want to address is this: who is responsible for language change? Okay. Before I do that, I need some time for some more for the introduction of a data set. So a couple of years ago, when I was reading through the epi literature, I came across a database called Polymod. I do not know if you know it. To me, it was new. It collects about 100,000 data points of physical contacts between individuals from 8 European countries: Italy, Germany, Luxembourg, and so on. And crucially, it also features demographic metadata, in particular information about participant age. Okay, the distribution of these contacts is visualized in this 2D histogram here. So what do you see? So here on the horizontal axis, you see participant age, so the age of the participant that was asked, and on the vertical axis, you see contact age, so the estimated age of the contact of that participant. Okay, the more green, the higher the contact rate, and the more purple, the smaller the contact rate. Okay, and what you typically see when you look at contact patterns, epidemiologists refer to this as mixing patterns, like this, is a particular pattern, namely a diagonal here. Okay, so a dark green diagonal here. And this reflects that we tend to be in touch with our peers, right? But what we also see, interestingly, is sort of two diagonals, two smaller diagonals parallel to the one in the middle. So this one here and this one here. And what these two diagonals reflect is that the parent generation interacts more strongly with the child generation than with the generation between. Okay, so how can we make use of this? The idea is to set up a model as before, but now with multiple age classes, and to inform the model with plausible contact data, demographic data, and data about cognitive processing of words. And then finally, I want to use this model to predict the trajectory of users for each age class. So there you go. This is the final equation for today. It looks very similar to the first one. However, now we trace change in the number of users in each age class I. We have 8 age classes in total. And the right-hand side essentially shows that individuals of classes I and J meet at a given contact rate, that non-users in class I can become users whenever they meet some other user, and that this happens at a certain rate of adoption here. So this is this beta parameter, which is constant at this moment. I need data to inform my model. I use the Polymod database to inform contact rates. I use data from the United Nations to inform this parameter here, which corresponds to the age distribution. And when you then make predictions, theoretical predictions, the trajectories look like this. So each trajectory here, so this is time here, this is prevalence per age class. Each line here corresponds to one age class. And what you see is that irrespective of where an innovation starts, adolescents are the fastest to adopt it. Okay. Now, hold on for a second. We can add a bit of cognitive realism. we can inform the model, namely the adoption rates, by using age-structured experimental psycholinguistic data, and this reflects that children and also adolescents actually display slower lexical processing than adults. How do the predictions change? Well, the more weight you put on this differentiation here, the more you end up with a scenario like this, where the roles of parents are promoted and the roles of children are demoted. So children are the lastest to adopt a certain innovation. And of course, this adds to the discussion about the interaction between age, structure, and language change. All right, let's wrap up. So we have seen that although these mathematical models that I used here are in a way simplistic, they also reveal interesting insights, theoretically, analytically derived insights about the average number of innovation transfer events, R naught equals about 6, drivers of semantic diversification, low frequency, non-conformism, discriminability, and also the relevance of adolescents and parents. And crucially, all of these results were derived analytically from these models. However, for informing and evaluating these models, what we need is data. A combination of diverse data, actually. So a lot of psycholinguistic data sets, surveys, experimental data, corpus-based data, texts, data frequencies, models, embedding models, for example, and also socio-demographic data. So data about contexts and age distributions, for example. All right. Now, the thing is that none of these data were actually created specifically for my studies. All of them were reused. But of course, this requires availability, interoperability, and also a proper documentation of these data sets. Now, I know that it is still some time until Christmas, but if I need to put something on my list of wishes to the Christkindl that we have in Austria, it is, first of all, make your data open, use cross-disciplinarily common data formats rather than specialized conventions that are only established in your own discipline, and also provide meaningful and easy to understand documentation and metadata so that other people who are not experts in your domain can also understand what your data are about. And this is because you never know which colleague from which other scientific discipline is going to make use of your data in their research. And in this way, we sort of also avoid that our data gets dumped in a monodisciplinary garbage bin. Thank you.
Thanks for your talk. I have a full 3 or 4 questions, but all are about the mathematical framework that you used. Can you show me, please, again, the first question? There is any particular constraint on the sum of the user and non-users? First questions. The second, when you speak about the competitions of 2 x and y, I see only one equation, but I imagine there is the counterpart of the equation. And if you study something about the stability of the ODI systems, if your model show any coexistence between users and non-users in a sort of the equilibrium state. So there is no more changes in that's all. Thanks.
Thank you for the question. So all of them are actually very good. So the first one is about the simplification in this model, namely that population size in this model stays constant. So no demographic growth in this part of the model. Yeah, I mean, of course, one can also look at total population size dynamically. This makes the whole analysis more complex, but yeah, so this is one constraint. The second question, I think, was about the competition between different variants. Yes, of course. So these details I actually did not show you on this slide. So the thing is, you actually see all the details in this paper here. But so the thing is that you sort of have one equation per variant, and the equations then also do not look exactly like this. But they depend on the semantic difference between the different variants. It's a bit more complicated, but yes. So that there are multiple equations. What was the final question? The equilibrium. Yes. Well, yes. So what you can show is that. Depending on what the parameters look like. So very often there are parameter configurations that yield a stable coexistence of users and non-users. So actually, what we hardly ever see with these models is that the whole population uses one particular variant or lexical item, let's put it like that, but that there are also people who do not use it, okay, and stably so. And this can also be shown with these models. And of course, I mean, this is what you can derive mathematically, but also empirically, I think it makes sense. So there will always be individuals that use different variants. Of course, so models like this work best when you look at innovations that are not shared by the whole speech community, because some of these equations do not work when prevalence is 100%. Okay, so this would be my very short answer.
Thank you. Thank you. We have some other questions. Yeah. Vincent? It was just Vincent before, and then Martin. Thanks, Andreas.
Okay, thank you for your talk. I have a few questions or remarks. One is, you do not seem to use any of the lexical properties of the word itself, or the meaning, or the innovativeness of the words, or you only seem to use external factors. Don't you think that the innovativeness or the funniness of a word plays a role in this?
Yeah, very good question. In this second model, which is about the competition, so actually this one here, I do look at lexical properties, actually, so a semantic property, but a unidimensional one. You know, so there is the idea is that with this simplistic model, you have one dimension that corresponds to one semantic dimension, such as valence or concreteness, or if you like, funniness or so. And as long as you can show that the adoption rate in some way depends on funniness or valence or whatever, so as long as the adoption rate is influenced by that, and as long as there is a maximum obtained at some point, this model will work. So that it will not work if there is no relationship between propagation and your semantic trait.
Yeah, so that brings me to my second question. How can you evaluate this? Like, can you experimentally test it with trying to launch some words and then predicting, as you seem to have a good model to predict what will happen with the spreading of the word?
I'm very hesitant because this model involves a bunch of different parameters, and most of these parameters are difficult to estimate. But very often coming up with exact predictions of what the future development of something will look like is not the primary purpose of models like this. The purpose rather is to test what is possible and what not. So these are in a way, theoretical models. They tell you, well, okay, there exists a certain threshold for non-conformism, for frequency, whatever. And if you go beyond that, then this is going to happen. They are, in a way, so models like this are sort of machines to reject hypotheses, if you like. And yeah.
Thank you. Martin?
Thank you. Your title and your conclusion refer to open data, which I'm very pleased about. I noticed, however, that the main linguistic data set that you cite is the corpus of historical American English, which, as far as I know, doesn't tick many of the boxes for the kind of the gold standard for open data, for fair data. It's not generally available for download. It's discoverable via word of mouth. It doesn't have a standard license. So I was wondering, were you able to do your research with that degree of openness?
I mean, so absolutely. I would say that maybe only, I don't know, 10% or 20% of the data sets that I have used here are fair, which is very unfortunate. But still, I mean, this is my wish list, so I can wish whatever I like. Yeah, and of course, in an ideal world, all of these data would be available for everyone. And it seems that I mean, why did I add this concluding remark? Because I find that it's super important to also have this cross-disciplinary communication. And this data set, so this contact data set that epidemiologists use, I mean, the EP people, they typically use software like Stata or so, and of course they could have used a Stata format to publish their data, and most of the researchers in epidemiology would have been fine with that, but they have decided to just publish it as a CSV. And as a matter of fact, there is also now a database. Now it's good, like it's already 8 years old, which systematically collects contact data like this. Yeah, of course, there is a lot that we still need to improve. And I do not say that all the data sets that I used are open, unfortunately.
Thank you. Andreas, we will take a last question, please.
Yeah.
Thank you very much for the presentation. I learned a lot. I wanted to ask about the child data that you used. You mentioned age of acquisition, but what I'm aware of is that age of acquisition has been reported by adults who report at approximately what age they think they learned a specific verb form, which is not trustworthy, and it's not aligning with actual child data from Childes, for example. So I was wondering, how would you account for that, or whether you could rerun things with data, spontaneous speech data from children?
Extremely good and important question. So the short answer is yes, I use exactly data like these. So those are subjective age of acquisition ratings where adults are asked to report at what age they have learned a certain word. These data show bad correlations below the age of 5 or so. Beyond the age of 5, it's getting better. So for this, it's getting more reliable. What I need to say is, to sort of defend my research here, I looked at innovations. So that the lexical items that I looked at were innovations. Lexical items that have spread recently, and most of them are not acquired very early. So most of them are acquired, I don't know, maybe at the age of around 10 or 12 or something like that. And there our estimates are more reliable. Okay, this is the first part of the answer. And the second part of the answer is that one strength of the models like this is, and of the fact that we look at equations here, in order to estimate something, that you can also run sensitivity analyses. So you can also check to what extent your estimated R0 value is sensitive to variation in the age of acquisition ratings. And I think this is good that we have this possibility and that we can put numbers on this uncertainty.